So she has got some. So I think they may have been affected a bit by other people running. Well, actually, no, that's an. Okay, yeah, okay. No. I think you're unstriped. Yeah, the first one's a bit low, but I think that they're actually very interesting. Okay, so so they're very interesting, actually, very interesting. I think I understand. And what I will do is I'll just show one set of results, and we can discuss them, and we'll see if they correlate. So yes, they're very interesting results, actually, that she has got there. But I just want to. So I ran the benchmark with 8 nodes. And these are the nodes we have, and I just did this as I suggested. Local array size is 128, 128, 128. It's 1024 processors that chooses to go 8 by 8 by 16. So the global size is that, and total amount is 16 gigabytes. So I'm doing MPI-IO unstriped, striped, and full striped. So MPI-IO on unstriped gets about 1 gigabyte a second. Now, there's going to be a small overhead from doing MPI-IO, but basically, if I get that rate, what does it make you think? If I'm getting only 1 gigabyte per second, what do you think MPI-IO is doing there? Anyone have any suggestions? Where have we seen this 1 gigabyte figure before? Anyone have a yes. So what, I'll come back to this later, but what MPI-IO is doing is it's allocating a subset of processes to be. Remember, I said that it can collect data together and then write it out. What it does is it allocates a subset of the MPI processes to be what it calls aggregator processes. And what it is doing is it is picking one process per stripe and putting them on different nodes. And so what we're seeing here is that we're only seeing 1 gigabyte per second because there's one stripe that only picked one IO process. Sorry, I've now done something silly. Now when we did on 2 processes, my striped had 2 stripes. So it picked two processes, and we got 2 gigabytes per second. With the full striped, it was using 16. So there's 2 things which are disappointing about this. One is it's clearly not optimal to pick. So on Archer, this would have been the sensible thing to do. On Archer, the balance was such that a single process could saturate the entire I/O from a node, and so you would want to pick one. You want to pick one I/O process per node. But what it's doing, and we'll talk about this later, is it's picking what it's trying to match the number of stripes, which is the number of OSTs. It's basically got one process right into each OST. That's what it wants to do. It thinks that's the optimal thing to do, not realizing that actually on ARCHER2, a single process cannot even come close to saturating an OST on the network bandwidth from a node. And this you would hope would be 12, but we only have 4 here. So these numbers are quite disappointing, but we'll come back to that. Okay, they are quite disappointing, and these correlate. If I look at Xiao's numbers, you got 0.96, 1.9, 5.5. Okay, so they were very similar to these. So they're not particularly impressive. So that's a bit of a shame. But we are achieving true parallel I/O, and you are seeing how we are benefiting from striping. Okay? We are benefiting from striping. Okay, haven't changed the code at all. By one command, LFS set stripe minus C minus 1, we've gone from 1 gigabyte a second to 5 or 4 or 5. So striping is helping us here. That is useful to know, but it's not doing. So what I will do now is talk about configuring the I/O system. As I said, almost all the things I'm talking about in terms of configuring the I/O system will apply to other libraries, and we can try this later, such as HDF5, because they will call MPI-IO at some later level. So I just need to find the right presentation. So James, do the output directory be made in advance of running a program? What do you mean by running a program? I mean, obviously they have to exist when the program runs, because otherwise there's nowhere to write them. I don't quite understand your question. Sorry if I'm being stupid.
I think I mean, can you make a command within a program to make the striped directories?
So do you mean like a C or C++ called Mukdir, or do you mean from a shell script?
Yes.
Which? Sorry, both.
The first, for like a call.
Oh, I would. Well, that's a good one. I would just do a system. You know, system LFS. There'll be a way of calling a system call from a C program.
Okay.
I would just do system LFS set stripe. So you would have to do an LFS command, but you would just Mukdir. And then you could do a system command, just pass a string and call a system command from the C program. Does that answer your question? I think you would just effectively. The natural, I mean, what you also might do is you could create them in your Slurm script. You know, the Slurm script is just a set of bash commands. So you could create them in your Slurm script as well. But if you did genuinely want to create them from your program, you would have to issue. There will be an API for Lustre. There will be an API which you could look up. I don't know it. But if you know the shell command, you could just do a system call. Make sure you're going to do it from one process, though. Don't want all 1,000 processes doing it. Does that make sense? So there will be an API. I've never used it myself, but I would have thought it'd be easier just to do a system call. Is it system of? Something like that. I guess that's going to work in most. That's a good question, actually. So I'm going to try and share content. Actually, I seem to be fairly. I am recording, which is good. So I think I originally called this configuring the Lustre file system. It's not all about configuring it, so I've kind of renamed to efficient use of the Lustre file system. So please ask questions. Don't worry if you see the numbers on the slides jump. It's because I have some alternate slides which are hidden. That's the only reason they went from 1 to 3. PowerPoint's very stupid actually with that, that it doesn't keep them, it doesn't do the numbering properly. So the question is Lustre, where are the bottlenecks? And I think actually we found out that the bottleneck from a single process is about 1 gigabyte, 1.2 gigabytes per second. For the processes on a node, it seems to saturate about 14 or 15, which I presume is to do with the network. I'm presuming that's something to do with the network. And we saw that these seem to be, we didn't get definitive answers because people got different numbers, but they were of order 4 to 6 gigabytes per second for a single OST. That seemed to be, I have some numbers I can look up, but that's the kind of ballpark I was getting. Someone got more like, it's that kind of number, 6 or 7. So, you know, depending on what you're doing, the bottlenecks are in different places, but it is clear that a single node can sat OST. That seems to be the. So caution, I maybe should have put this earlier. IO benchmarking is very difficult, can be non-reproducible. You are sharing the ARCHER2 system with other users. Someone else may also be writing the same OSTs. Someone else may be using the same network links. So, you know, you share on Archer, you always get exclusive access to all the processes on a node, which is nice. You have exclusive access to the memory, but you share the network with other people, and you also share the disks, physical disks with other people. And so I saw that Jiao's, I probably if I'm pronouncing your name wrong, Jiao's numbers, you know, the first set of numbers, some of them look a bit low, but that's because, you know, you would have been running, well, maybe I was running at that time. Caching can give very high I/O rates, especially with small files. Actually, this isn't as bad as I thought. I thought I was getting unrealistic I/O rates on ARCHER2 due to caching. It's actually that the OSTs are much faster than I thought they were going to be. So when I was getting 80, 90 gigabytes a second, as some people have reported here for single process, for a file per process, I assumed that was due to caching, because that was the only way you got anywhere near that on Archer. But actually, it appears to me that actually that is a genuine I/O rate. Ensure benchmarks run for a reasonable time, e.g. a few seconds. That's why different benchmarks I've got in the exercise have different sizes of data, because you need to run for, there's no point running for minutes and minutes, but you don't want to run for under a second. And repeat them several times. If you really, really wanted to bottom this out, you'd run them several times at different times of the day, and maybe pick, well, you could pick the maximum if you're interested in maximum, or the median or something. But I/O benchmarking is very difficult. It is like saying how long does it take you to get to work on the bus. It's sort of a meaningless question, because it just depends. 30, 35 minutes on most days. Might be lucky one day, and another day there's a traffic jam and it takes you an hour. It's that kind of question. I always think traffic and are very good models. Traffic and driving are very good models for computing on a whole bunch of reasons. So the ARCHER hardware, just to reiterate, 3 separate work files, as we appear to be on work 3. Each has 12 OSTs and 1 MDS. We've seen the OSTs can support actually more like about 8 gigabytes per second. We haven't consortium that. So this SSD will be interesting to look at. And so we have about 3 petabytes of storage in each one. So serial I/O, you're not using parallel libraries. So you might be doing single file with a controller I/O or file per process. There's little point in striping the file. In fact, I think striping the will actually, we can try this, but I think striping the file with file per process will harm you, because every time it does access, it has to contact the MDS and say, it's more complicated. You actually want, if you're saturating if you're filling all the OSTs because you have many files, there's no point complicating things by striping those files over the OSTs. That will just make things worse. So I think, and I haven't had a chance to check this, it's definitely true on Archer, that little point in striping the file for what's what appear to be elsewhere. Multiple files already parallel, as we're using many disks. So if you've got a single file, there's no performance striping because the bottlenecks appear to be elsewhere. What I mean is that you can only do a gigabyte per second for a single process. So multiple files, there's no point striping them because we're already parallel using many disks. This is why single stripe is the default, because a lot of people don't do parallel I/O. Ballpark figure, single process can achieve about 1 gigabyte per second, which we've seen, slightly in excess of that. MDS performance, the MDS can become overloaded. Only enclosing a file requires MDS access. This is there for a serial operation. It's interesting, actually. I want to show you something here to maybe it's quite interesting. So you'll see if I share, I'll share a different screen here. This is my laptop, okay. I'm in bench IO, okay. If I do ls, yeah, you'll see that my files are colored nicely, that the directories are blue, make files are green for some reason, and I think executables are maybe red. I can't remember what they are, but anyway, we get nice coloring. But if we go on to, that's on my laptop. If we go on to ARCHER2, you'll see that I've colored my cursor, but if I do an ls here, it's up. There's none of this coloring with the where are the, and the reason. Whoops, I didn't mean to do that. That's something weird. That's something very strange. Okay, the reason is that inquiring about like, is a file, is this a directory or not? Is it executable or not? What type of file is it? Requires MDS access. You have to contact the MDS. And on Archer, the default setup where Linux LS, if you do, often on Linux systems, Linux is list to alias to ls minus color equals auto. That meant if you listed a directory with 1,000 files, it had to look up the MDS 1,000 times, and that was killing the system. That simply coloring the files based on whether they were directories or executable or plain files was killing the metadata server, because every time someone did an ls, it had to contact the metadata server. Now, I didn't do a terminal change there actually, but I will do it. I thought about it and then didn't do it, so I won't do that. I appreciate that was I will switch to what are you seeing it now? You should now see my give me a second. Do you see something there which says ls minus color equals auto? Is that okay? Yeah, fine. It was my fault. So actually, this is a complete travesty. This is Ubuntu. Ubuntu alias is the ls command. That is a total no-no. You should never, ever, 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 ever. It's been a tenet since Unix was invented in the 70s. You do not alias Unix commands. You do not alias Unix commands. But they've done it because they wanted the colors to be there. It's a shocking thing to do, but there you go. That's the modern world. Sorry, but anyway, that had to be turned off, which seems incredible. But yeah, just so that won't probably be true on Archer 2. We've still turned it off on Archer 2. Archer 2 is much better. The MDS on Archer was very underspecified because Archer was an old system and it got out of hand. So we had to do various tricks on Archer, and I've now lost my windows again. I want to do Windows. So tricks. So opening and closing a file requires MDS access. There's one MDS. This is there for serial operation, serialized, and you share the MDS with all users on the same file system. So if you open 1,000 files, the MDS has to go through them one at a time. Once you're actually doing I/O to them, you're okay. But opening and closing them is a serialized operation. Normally that's okay. You might pay a bit of overhead at the start, but do not do multiple open seek close operations on the same file. There are some applications, and one of them is OpenFOAM, which in a certain configuration will have thousands of open files, and when it wants to write to them, it opens the file, seeks to the end, appends, and then closes it. And that's not OpenFOAM, that's something else. I think it's CASTEP. Anyway, don't do that, because that means that is just a nightmare. Don't open the file, write to it, close it. Don't do open seek close operations on multiple files at the same time. It's a nightmare. Tricks: if you are overloading the MDS, try not to write too many files. A simple trick is file per node rather than file per process. That's it. That would be it. Although actually, of course, we saw that you need multiple. You probably need about 12. You need about 12 processes, right? But maybe 12 files per node rather. But at least that cuts it down by a factor of 10 at least. Have a way of saying, I'll not write one file per process. I'll group them up into groups of. I'll write a file per 8 or 16 processes. And if they're on the same node, then that collecting the data doesn't cost you a lot because you're not going over the network. If you must have lots of files, consider multiple directories, e.g. a directory per node. Looking up files can be difficult. It's a linear process. So actually having multiple directories, when you're looking for a file, trying to open it, for example, it's quicker. Because if you have multiple directories, each directory only has about maybe 100 files. So you have to scan through 100. If you only had one directory, you might have 1,000, and that would take 10 times as long. So I don't think MDS load is going to be an issue in Archer 2, but I might be wrong. Stripe size, default is 1 megabyte. That seems quite small for very large data sets. If you have gigabyte data sets, that's 1,000 stripes on. I mean, as I said, parallel file systems are optimized for writing large amounts of data. And so if you have a stripe size of a megabyte, I guess you're writing a megabyte at a time. It's not a huge amount. You can experiment with larger settings. So LFS set stripe minus S, say 4M, might help you. Don't set it too large, as you won't be using all the OSTs. If you had a 128 megabyte stripe size and a 256 megabyte file, you would only ever use 2 OSTs, even if you tried to stripe over more, because it would run out of space. But that 1 megabyte might be slightly be looking a bit low. I haven't played around with this much. A colleague of mine, Michelle, has, and she's seen benefits from larger stripes. So how does parallel I/O work? Well, MPI-IO auto-configures to the Lustre settings, and it identifies a small number of what they call aggregator nodes. So what it does is it identifies a subset of the nodes. Well, actually, not aggregator nodes. That is wrong. Aggregator processes. So apologies for that. That's a mistake. Processes. It tries to spread them across nodes. So I should actually. So actually, it's slightly complicated, but sorry for that mistake. Identify a small number of aggregator processes spread across nodes if possible. It uses MPI collectively to scatter or gather to aggregate data to these processes. And then it performs a small number of large write operations, minimizing the overhead of locking, etc. So this is what it does with collective I/O calls. You can actually get useful runtime statistics by setting this magic variable MPI-CH MPI-IO stats equals 1. That will tell you, apologies for the typos here, that will tell you, for example, how many aggregators there were, and it may tell you where they are, I can't remember, but it definitely tells you how many aggregators you have. Now, what it actually does is, so why this is good is, for example, if I had 4 stripes, which I'm going to say is 4 disks, disk 1, disk 2, disk 3, and disk 4, in my default example of a 4x4 and a 2x2 process grid, basically, if I have a process doing a response for disk 1, it collects all the data together and does a single write. Process response for disk 2, it can write all that data, disk 3, disk 4, and so there's no clashing. Each process is writing to a separate disk. If I did the I/O independently, then this yellow process would have to write to disks 1 and 2, and it would clash with this. So what you're trying is trying to match the number of writers to the number of stripes, although we've seen actually that may not be the optimal thing to do, but that's the idea. So that basically processes aren't clashing when they're writing to disk, to the OSTs. Now, by default, Cray MPI uses 1 aggregator per stripe. That doesn't seem optimal. We've seen that single process. I really apologize for my typos here. I/O is slow. So this can be changed with a very, very strange syntax. X for MPI-CH MPI-IO hence equals star colon Cray CB knows multiply equals 2. It's a very bizarre syntax, but I think that is probably going to help us, because we have seen having a single process writing per node is not ideal, is not optimal, and that's why our baseline was like 1 gigabyte per second. It went up to 2, but we also saw that it went 1 gigabyte a second on 1 stripe, 2 on 2, but only like 5 or 6 on 12. Why was that happening? Well, there's another thing going on, is that the default low-level network layer uses something called OFI, Open Fabrics Interface, and this can sometimes have poor MPI collective performance. So the aggregators, what they're doing is they're using MPI, normal MPI not collective I/O, just normal collective routines, gathers, for example, to bring all the data together, and then they're writing it out. If that gather can take some time, and for some reason, which we don't quite understand, the default implementation of MPI on ARCHER2, which uses something called the Open Fabrics interface, can have poor MPI collective performance. Now, I'd have seen there was a magic variable in the script, export FIO, RXM SAR limit equals 64K, which alleviates this to some extent. However, there is an alternative version of MPI which uses a different low-level network layer called UCX, which is Mellanox specific, and it seems to be better for collective with heavy comms loads. So no need to, if you want to try this new network, this new MPI thing, you just do a couple of module swaps for you. So you don't need to recompile. You just do this at runtime. In your Slurm script, use a different MPI implementation, and you can try and see. And I think my experience on real codes I need to check on is that this will extend the scalability out quite significantly. So common mistakes we see serial I/O mistakes, text data files. I mean, yeah, do not write text data files. If you've got data, if it's numbers, write it out as raw binary. There's two reasons why. Text bloats. You know, an 8-byte double position number will be needing many more than 8 characters to represent it, even semi-accurately. But of course, you're also doing all the conversion. You're having to convert from binary to ASCII, which is going to kill you. Multiple access is a large number of small files. That's often this, you know, open, seek, write, close on thousands of files. That's a killer. And we said using striping for serial I/O. You know, if your serial I/O do not want striping, it doesn't help you. It won't help you if you're doing controller I/O. It will probably hinder you if you're doing file per process. Parallel I/O mistakes. The biggest one is using a parallel I/O library but typing the file. People say, look, I've got parallel HDF5 and my I/O performance is terrible. Well, one command, lfs set stripe -c-1 output directory, can multiply the I/O speeds by order of magnitude. So, and I would also recommend full striping across all OSTs. On Archer, our previous machine, we had 50 OSTs, so full striping was quite heavyweight. 50 is a lot, but here we have, so sometimes you maybe wanted to go a halfway hash, but I think really here, you either, I would recommend either non-striped, stripe count 1 for serial I/O, and full striping -1, which is 12 OSTs for parallel I/O. The other parallel mistakes is using non-collective, i.e. individual I/O to a single file. At least on Archer, that had made your I/O 10, 100, 1,000 times slower. You're getting megabytes per second. It was atrocious. In general, people are quite poor about quantifying their I/O. They'll come to you and say, my I/O is very slow. And you'll say, how fast is it? They'll say 3 minutes. That's like saying, it takes me 10 minutes to get to work. I've no idea if that's good or bad. Don't know how far your work is. You need to quantify it in gigabytes per second. You need to say, my I/O is achieving this. And I've written here, you should be able to achieve around 10 gigabytes per second for parallel I/O. I mean, this figure came from investigations I did in the early days of the ARCHER2 service, the end of last year. And it was when I didn't understand that I didn't understand the aggregate issue. So I think you might be able to get more than that. But that, you know, that's the kind of numbers you should be getting, tens of gigabytes per second, not single gigabytes per second. You should be getting tens of gigabytes per second, or 10 or so. I don't want to be. I'll learn more in the coming months. Conclusions for parallel I/O to a single file. Use a high-level parallel I/O library. We've talked about MPI-IO, but you could use NetCDF or Adios is this other library. Use collective calls. I'll cover what they are very briefly for HDF5. And stripe file across all OSTs. LFS set treat -c-1 for serial I/O, single or multiple files. Do not stripe the files. Just accept the defaults. Consider writing a file per node. Because controller I/O uses a single disk. File per process may overload the MDS, especially with many users. Actually, I should say multiple files per node there, because we've seen that it depends how many nodes you have, of course. If you had 50 nodes, then file per node would be fine, because you'd have 50, 60 gigabytes per second bandwidth, which seems to be, it depends, but you know, you want to have a way of tuning, having only a subset of your processors doing I/O, and if you have those subsets aggregators, they all live on the same node, and you have subsets of 16 on the same node, then you minimize your communications overhead, which is good. So the exercise I had now was really to look at trying some of these things. Exercise 7, you know, maybe set the IO stats equals 1 to try looking at the stats, increasing the stripe size, and trying the new MPI library and trying the multipliers. So those are things which are definitely worth doing. I'll be playing around with them myself. But are there any questions that people have? Is this a maximum file size? I suspect not. Well, there will be, but it will be 2 to the big number. So I suspect it will be. In the old days, of course, it would have been 2 gigabytes or 4 gigabytes, which is 2 to the 32. I suspect it. I'm guessing it's 2 to the 64 bytes. What's 2 to the 64 bytes? Oh no, that's gonna. A gigabyte is 2 to the 32. Sorry, a gigabyte is 2 to the 30. So a terabyte is 2 to the 40. So if a petabyte is 2 to the 50. It might be whatever. I would guess it would be 2 to the power 63. I'm guessing, but they may have taken that limit away. I would guessing. It will be 64. I'm guessing, and that's a good question, but I'd be absolutely astonished if it wasn't at least 2 to the power of 63, which is I should be able to do this, but I can't. Which is it's 10 to the 19, which is quite a lot. Oh, what's that? Yeah. I can now get lost, but yeah, exactly. That would be my. In the early days of Lustre, there was that the file sizes could be infinitely big. Sorry, arbitrarily big, but the quotas were done in 32 bits. I should know that, but I don't. That's a good question. Yeah. Yeah, very big. 2 to the 63 is 10 to the 19, which is, oh dear. I should be able to work this out, but I can't. I'll need to think about it. 10 to the 6 is a meg, 10 to the 9 is a gig, 10 to 12 is a tera, it's a peta. It sounds like thousands of petabytes to me. Yeah, sounds like thousands of petabytes. Should be okay. You do have to be careful though, with big files. It's very easy in your code to use integers for things like byte offsets, which can be, you know, a 32-bit integer can't be bigger than 4 billion, which isn't very big. That's only 4 gigabyte file. So you do sometimes get if you've done something stupid, if you've done something a bit silly yourself, you may find that your code fails on large files if you're doing seeks or whatever and not storing the offsets in large enough variables. But for the actual operating system, I would be astonished if it wasn't any smaller than 2 to the 60, if it were smaller than 2 to the 63. It's a long integer. Okay, so we do actually astonishingly seem to be on time. I think that if I look at the timetable, yeah, I wanted to play around with these till about 3 o'clock, and then I'll do the final lecture at 3, and then we can have a break, and then I'll be around after the break. And there are some further exercises. You can use the benchmark to do HDF5 as well. I would like the benchmark also to be able to do this new library called Adios, but I haven't implemented that yet. I maybe need some help from some colleagues. I know Shrey, who might be on this call, has done some Adios stuff. I can maybe copy the code he's written. Final lecture is just on alternative parallel I/O libraries. This is very brief, but just to give you some idea of what's available. So what are the issues with MPI-IO? Oh, I've got availability on 0, so that's a typo from my previous course. HDF5 and NetCDF in summary. So MPI-IO issues, the files are just raw bytes. When you write an MPI-IO file, it is just the raw data. There's no header information, and if you use the native format, the storage is architecture specific, so you'll get this usual issue with big little endian floating point. It's very difficult to deal with in other codes downstream. If I wrote a large MPI-IO file, gave it to somebody to visualize, they wouldn't know what to do. The user must write their own post-processing tools, but it can be very fast. So what people have done is they've come up with more flexible and self-describing data formats which have metadata, which means that you can visualize them because the file then knows what it represents. It would know it would represent a 3D array of double precision numbers. So for functionality, you define higher level formats which include metadata. This is a 4x5x7 array of doubles, and that means you can have standard data converters, browsers, viewers, etc. So it's much easier. But for performance, the people who write HDF5 don't want to re-implement parallel I/O, so they layer on top of MPI-IO. So many real applications use higher level formats, but understanding MPI-IO will enable you to get performance as well. So HDF5, I'm not an expert, but it stands for hierarchical data format. Set of file formats designed to store and organize large amounts of data. It's arranged like a Unix file system. It's self-describing, hierarchical, can use MPI. So it's very, very sophisticated. You can have, it's not really a file, you can have whole hierarchies within it. But the main thing is it has metadata and it's self-describing. So you can ask an HDF5 file, what are you? And it will say, oh, I'm a 512 cubed array of doubles, for example. So the approach is much like MPI-IO. You describe the global data set, then each process describes its local portions of the global set, then call a collective write. But at least for structured data, HDF5 calls these hyperslabs. So MPI called them subarrays, and HDF5 calls them hyperslabs. So that file space is to do with your global data and encodes all the sizes of the global file. H5 select F is the equivalent of MPI order Fortran. This is a Fortran program, tells it it's a Fortran code. The offset is the starts, where in the array, this subarray or hyperslab, this HDF5 calls it starts, and the count of the subsizes. So it's the same information but passed in a different way. But then these are then converted into MPI-IO syntax, and under the hood it uses MPI-IO. NetCDF is used by the climate community of array-oriented scientific data, so it's more restrictive than HDF5, but designed for climate data and oceanography because it's for regular data. So, for example, we've got the daily temperature across a grid across the globe, and that can be stored as a NetCDF. And again, there's a rich set of tools for data manipulation and visualization. So again, parallel NetCDF, Fortran, you have a file identifier, and you pass it this NCID is given back to you, but you say it's doubles, and these are the sizes. And then when you do, oh, I should have said previously, apologies. The other important part of the HDF5 was that it was Oh, you call a collective write, sorry. So in HDF5, you call a collective write. That's important to use call a collective write. There will be non-collective and collective writes, but it's important to call a collective write. For NetCDF, we have a file identifier. These are the sizes. Then that's for doing like a light all. And then we have these are the starts and these are the subsizes. So again, HDF5, you pass the same information. The size of the data set with these dim IDs, the starts and the counts, which are the subsizes. Again, the NF put var par access tells you it's actually the write. We have an NF90 collective, which is the equivalent of write all. So again, different syntax, but the concepts are the same. You open a file, you define what subarray of the whole file you own, what subset each process owns, and then you do a collective write or read. So it's a very short talk. The summary is that MPI-IO may seem a little low level, but it's fundamental, the fundamental building block of parallel I/O on most systems. Higher level formats layer on top of MPI-IO to benefit. So people do, Cray are tuning MPI, HPE are tuning MPI-IO to work well with their Lustre. Therefore, you want HDF5. You don't want to have to re-implement that. Common formats are HDF5, NetCDF, maybe less common, but used by the climate and weather and oceanography community. You might also want to look at the new IDOS2 library. I don't know if we have that on HDF on ARCHER2 yet, but we should. IDOS2 is a very new library, and it has a number of features which I understand. Okay, yeah. Kevin says that IDOS isn't available. We should look at getting it on there. Its interesting features are you don't necessarily have to write to file. You can use it to communicate. You can basically, one option is to write to file, but you can also say don't write to file, send the data directly to some other program, and that's kind of seamless. That's good. The other thing is you can have the same IDOS calls, but at runtime say, I want you to write using MPI-IO, I want you to write using HDF5, I want you to write using a native IDOS2 library. So you can actually select, without changing the code, I think there are environment variables, you can select what the output layer is, which is much more flexible than hard coding HDF5 or MPI-IO in your code. But still, understanding MPI-IO performance and how it interacts with Lustre is key to getting good performance for HDF5 and NetCDF. And all these settings like stripe sizes, aggregator nodes, all these things will affect MPI-IO, which will also have hopefully beneficial effects on things like HDF5, NetCDF, and IDOS, which are all layered on top of it. So that was a very, very short talk to summarize. So we kind of finished a little bit early, but there is a final exercise, which is to repeat some of the MPI-IO experiments using a higher level library such as HDF5. You just basically, instead of saying MPI-IO, you say HDF5. It's interesting to see if the I/O rates are similar to MPI-IO. Is there any loss in this layering?